Welcome back, everyone, to this lecture on seaborne grids. Seaborne grids are essentially analogous to Matplotlib subplots call. And what they do is they automatically create a grid for the subplots based off a categorical column. So previously, we had to pass in a specific number of columns or rows for the Matplotlib subplots. But with Seaborne, what we can do is we can actually just pass in the name of the column that we want Seaborne to automatically map to the subplots grid. So many of Seaborne's built-in plot calls are actually running on top of this grid system, allowing you to simply define an extra parameter call for row or columns. And directly calling the grid system also allows users to heavily customize plots, specifically the pair grid that the pair plot runs on top of. So for example, we can take the current box plot call and then separate it out to rows and columns based off a subplot grid that Seaborne can run on top of. So here we can see the actual box plot now separated by further categories. Or what we can do is we can also map plots based off a pair plot grid. So pair plot underneath it is actually calling something called a pair grid system. And what we can do is we can directly access that pair grid system to map certain plot types to either the diagonal, the left bottom of the grid, or the top right of the grid. So all of this is really best understood through the code. So let's jump to the notebook and explore the data a little further. All right, here I am at the Jupyter Notebook. I've gone ahead and completed my imports, and I've also read in the student's performance.csv file. So there's two main different type of plot calls that we can use when we're discussing the Seaborne grid system. The first one is the cat plot call. So we can say sns.catplot, and if we expand on this, you'll notice it takes in an x and a y. And so this is essentially the statistical distributions within categories that we can begin to explore. But more importantly, it takes in these additional arguments of row and column. And row and column is actually what is going to define the subplot grid that is created below this. And then we just have to say what kind of plot we want. So you notice if you scroll down, there's this kind of plot you can create. And eventually you can read all the different kinds of plots that are available to you. You can do box plots, violin plots, box-end plots, swarm plots, strip plots, etc. So what I'm going to do is first explore this by saying my data is equal to df. I want x to be equal to gender, and let's say y is equal to the math score. And then I'll say the kind is equal to box. So you can imagine that when we call seaborne.boxplot, it's essentially doing this call, catplot, underneath, where it's specifying the kind to be box. So if I run this, this looks like a normal box plot call, except in this case, it's the more generalized categorical plot call with kind specified to box. So what's so special about this is that then I have these extra parameters I can call, which is row and call. So I can say row is equal to something. So I can say row is equal to, let's go ahead and say it's equal to the lunch column. And what this is going to do, it's going to take this box plot, but now it's going to create rows for every category of lunch. So then this looks like this. Here I can see the box plot for people that have a free and reduced lunch. And here I can see the box plot for people that have a standard lunch. This is really similar to setting hue equal to lunch, except now what it's going to do is create a separate subplot for each of these. So we're already familiar with calling hue to separate out different categories. And here we can see them colored being the main distinction, not the grid. But if I want this to be a grid, what I can say is make the rows equal to lunch. So here, each row for the subplot grid represents a different lunch type. Or what I can also do is say the columns are going to be defined by this. So here I can see each column in this grid is now based off some lunch type. And what's interesting then is I can then define something like row equal to whether or not the student took a test preparation course. So we can say something like test preparation course for the rows. And now we slowly start building out this, what is essentially a Matplotlib subplots call, but with a Seaborne grid. So instead of having to say, I want 2 rows by 2 columns, like we had to do with Matplotlib, I can simply define the columns and the rows based off categorical columns in my data frame, saving me a lot of work of having to figure out how many different types of lunch categories do I have, or how many different types of test prep courses do I have. So here then, it's automatically labeled so that we can see the top left corner is the distribution of the math score as a box plot where the test preparation course was done and the lunch is standard. And we can begin to actually create these grids. Keep in mind, if you create so many grids, it can be harder and harder to read the actual data. So I would suggest that a 2x2 is kind of the max size you go for. But again, it's always up to you how many different groupings you want to do. For example, there's actually many groupings here for race and ethnicity. So if we copy this and set the rows to race and ethnicity instead and ran that, you'll notice now we get quite a few rows. So this becomes harder and harder to read as you have to kind of scroll down or have your eyes jump a lot between the box plots. So always keep that in mind as far as what columns are appropriate to actually create the grid off of and how much harder the grid is going to be able to read. But what is nice about this is I didn't have to define beforehand how many rows I actually wanted. Seaborn does this automatically, which is a super powerful tool. And of course, you can edit the kinds to what we discussed before. So if you really wanted to, you could set the kind equal to violin, and then it's going to create violin plots for all of these different categories. And you can go ahead and check out the documentation string here for the various different types you can use. You can say a strip plot, a swarm plot, box plot, violin, box and plot. You can also then start doing things like bar plot and count plot, depending on exactly what you're setting for X versus Y. Okay, so all of that is available to you. Essentially, the way you should think about this is that cat plot is this kind of very base level call for all the different categorical plots that we understood before. And in general, you should really only be calling cat plot if you do plan on creating this column or row grid. If you don't plan on using this feature of columns and rows, I would suggest you go to the higher level abstraction of just calling something like sns.violinplot or sns.boxplot because they're a little easier to work with and understand. But both options are available to you. I'm going to comment all this out and move on to the other main grid type, which is the pair grid. So before, I already saw that I could say sns.pairplot, pass in my entire data frame, and what it does is it takes all the numerical features and automatically creates this pair plot data frame where we have the scatter plots as well as the histograms. So what's actually happening underneath is this is calling the pair grid functionality, which creates this grid and then fills it in. So what we can do here is actually explore that pair grid by saying sns dot, and then say, notice the capitalization here, pair grid df. And at first, it just creates the grid automatically for us based off the columns we passed in. What it's still waiting for are the actual mapping commands that it wants us to provide. So the way this works is you say something like g for grid is equal to this pair grid. So you run that, and you have that here available to you. And then what you're going to do is in the same cell, say g is equal to, and then you start calling this mapping commands. So you're going to have map underscore, and there's three main mappings. There's the upper mapping, there's the mapping for the diagonal, and then there's the mapping for the lower. So for example, I can say for the upper half of this, go ahead and map a specific plot type. And this is where you actually pass in relevant plot types. So I can say, go ahead and map a scatter plot. Keep in mind, the mapping should make sense for the plot type. So clearly, the upper mapping here on this upper triangle should be something that can take two continuous features and compare them x versus y. So we know a scatter plot can do that. So then if I map a scatter plot here, you'll notice now on this upper diagonal, I've mapped a scatter plot. And then I could do the same thing for the lower diagonal by saying g is then equal to g dot map underscore lower and choose another plot type, such as KDE plot, which I know can work for two continuous features. It's a two-dimensional KDE plot. So now when you run that, it's going to map a KDE plot to the lower half here. And then finally, we can specify what we want to be mapped along the diagonal. Keep in mind, the mapping should make sense for just a single feature since it's going to say math score versus math score. So for example, if I said g map diag is the call, I wouldn't want to say SNS scatter plot. Why not? Well, if I map a scatter plot to the diagonal, it doesn't make a whole lot of sense because there's essentially the same point types. So math score versus math score is going to be a straight line of matching. So it doesn't make sense to use something like scatter plot. Instead, it probably makes more sense to use either a histogram plot, so we can say something like histplot, run that, and that way I can see the histogram for each of these features, which is kind of the default. Or if I wanted to, I could explore this with a KDE. So I could say SNS.kde plot for the diagonal, and then I get these KDs along the diagonal. So this is essentially a way to customize the pair plot to whatever you want. It's not super common to have to go in and do a deeper dive into the pair plot or pair grid. Usually just calling pair plot is fine, and then calling a joint plot to further explore. But if you do really want to, for some sort of final visualization, create this pair grid and then manually map the upper, diagonal, and lower, it is available to you. And keep in mind, pretty much for all of these, they can pass in the other parameter calls. So for example, let's say I wanted to add in a hue setting for this entire plot. Up here in pair grid, I can add in those higher level parameters. I can say, go ahead and say hue is equal to gender. And then when you run this, what's going to happen is it's going to recreate that, but now it's going to double everything up based off the hue. One thing to notice here is, for whatever reason, it doesn't automatically add the legend, so you don't really know which color is with which color. So for that, you have to actually add in the legend manually. You'll say G is equal to G add legend. And so when you have a hue parameter at the top call, it can then add the legend for you. So obviously here, we're doing a lot more work than just calling the pair grid, but that does come at the trade-off of being able to customize a lot more. In general, we're pretty much never going to call pair grid throughout the rest of the course. I just want you to be aware that it is available to you. The last thing I want to note here is this cat plot, when you separate it out by column and row, it is actually technically running off another C-born grid object called an SNS facet grid. And I'm just going to show this with the lecture notebook instead of typing it out, because we really are never going to code this out ourselves. It's just more here for your information. So if I scroll back up here in the lecture notebook, we saw that I can call .catplot, choose a kind of plot, and then specify what I want the rows or rows and columns to separate it by some category. And what this does, you'll notice it says it's running off a facet grid. And that's because if we scroll down here, there is the facet grid object that if you really wanted to, you could call yourself and then create this facet grid and then start using the g.map calls to map things to this facet grid. Now, this is a lot more work for essentially the same plot. So I would recommend that you really only jump to facet grid if for some reason you're not able to create this particular plot type you want with a simple C-born cat plot type call. But in general, you should always be able to figure out a cat plot or C-born call or even a Matplotlib call before you're having to dive in to the facet grid. So here are some examples of how to use the facet grid. You essentially create the facet grid and start mapping plot types to it, which allows you full customization over the grid itself. But in general, we saw that the cat plot call is more than enough for what we're looking for. And then again, pair plot is probably more than enough for what we're looking for. We don't need to dive into pair grid and start mapping stuff ourselves. But it is all available to you, and you can check out the documentation online in case it interests you. So be aware that pretty much all these plot types is not something we're really going to be exploring, but there is this grid system available to you within C-born for your convenience. Okay, thanks, and I'll see you at the next lecture.